In this video, we will introduce the concepts and terms that we will use during our discussion on perception. Class time will be used to discuss and investigate the concepts in more detail. So, perception. Look at this figure. Is it pointing out at you or back into the screen? Your eyes are sensing the black lines on the white screen. There is no real depth, yet your brain tells you that there is. Your brain is perceiving. However, in this case, it can perceive two different things. Perception is the mental process of identifying, sorting, and arranging stimulus data into meaningful patterns. This image makes clear two crucial concepts about perception. One, it is not the same as sensation. And two, it's not always reality. When we process information, we go about it in two ways. If I handed you an object and asked you what it was, you might take into account its elements, shape, size, texture, color. You would feed that sensory input into your brain in what we call bottom-up processing. There, it would meet up with information you already know based on your experience. It would be primed by your expectation, and it would be colored by your emotions, all of which may compose the top-down processing. Where they meet in the middle is your perception. So what do we perceive? In short, we perceive that which we attend to. Right now you are being bombarded with information. Each of your sensory systems are constantly sending bits of information such as you couldn't possibly attend to all of it. So we selectively attend to incoming information. Here's an example, the cocktail party effect. It's your ability to follow one conversation among many. It's not that you're not hearing all the other conversations. All those sound waves are hitting your ears and stimulating neurons in your cochlea, yet you are only attending to one. However, if you hear your name being said by the gossipy partygoers behind you, you might quickly shift your attention and suddenly be aware of that conversation. You were hearing that conversation all the time, you just weren't attending to it. We have a difficult time attending to multiple things at once. In class, we will test this, plus our susceptibility to a phenomenon called change blindness, and we will investigate whether or not stimuli we don't notice can affect our decision making. We will also look at visual illusions and see that it's the visual system that tends to override our reality in a phenomenon called visual capture. So how do we organize our perception? Let's investigate the concept of Gestalt. Gestalt is the German word for the whole, or the form. We're going to look at the Gestalt concepts of figure and ground and of grouping. When we look at any image, we immediately kind of determine the difference between the foreground and the background, or the figure and ground. In this picture over here, we can either see a vase or we might see two faces, depending on which way our brain interprets the figure versus the ground. We'll look at a number of different illusions, but this is the first thing we do in our visual process. We distinguish the figure from the background. In the Gestalt concept of grouping, we'll look at a number of different things. First, let's look at proximity. What do you see here? Do you see 6 lines, or 3 groups of lines, or 3 columns? It's our tendency to see these lines in groups of 2 because they're closer together, proximity. How about here? The Gestalt concept of similarity. On the left side, do you see vertical columns or horizontal rows? What about over here? Columns or rows? We tend to organize our visual experience based on similarity, so on this side we'd more likely see columns, and this side's horizontal rows. The Gestalt concept of continuity. In this case, based on continuity, we might see one long continuous curvy line being bisected by a relatively straight line. However, in fact, these are distinct semicircles, but our brain doesn't see it that way when it's connected. Let's move on to the Gestalt principle of closure. This is a real interesting one. Here are 2 examples. When we see this image here, our brain closes the image, meaning even though it's not here, we see this line, or we perceive it. Maybe we don't see it, but we perceive it. And if I go back and erase it, we don't feel like this an incomplete image here. And over here, this is a very interesting illusion because it appears that there's a box in here, and that box is covering up the rest of the completion of these circles. But in fact, there is no box there, and there are no circles there. These are, distinct shapes. This has this shape. But our brain doesn't perceive that. Our brain likes to close the image, and based on what we expect to be there or our experience in the past, we see 4 circles with a square sitting over top of them. And finally, we have the Gestalt concept of connectedness. When we see pieces like this, we see a connectedness. We assume that these belong together, when again, in fact, they're separate pieces. They're circles and lines, but the ones that are touching, we kind of group together mentally. We kind of see them as one piece, even though they're not necessarily together. That's just the way our brain kind of interprets the situation. The next concept we're going to investigate is depth perception. A classic experiment done on depth perception, they have a plexiglass plate and create what's called a visual cliff. This baby is in no danger of falling, but he doesn't necessarily know that. So the question is, does that baby innately understand depth? Would he fear falling here? Our ability to perceive depth is very important in our visual experience. We have a couple different, or many different cues that we use to understand depth. 2 of these cues are binocular, meaning they rely on us having 2 eyes, and many more of our depth cues are monocular cues, meaning we could get away with having only 1 eye and still be able to perceive depth. So let's look at each of these principles. First, let's start with our binocular cues. The first of our binocular cues is called retinal disparity. This comes from the fact that because we do have 2 eyes, we actually are perceiving 2 different images of the world. Our brain sees 2 pictures at one time. And they're not the same because our right eye and left eye have a distance between them. So what our brain sees from our right eye is a slightly different version of the world from what it sees from our left eye. This diagram shows more clearly what's happening here, but here are 2 images or 2 dots that are the same distance, and our brain, the pictures on both of our eyes are relatively the same, but if we set these 2 dots apart, we see that the right eye and the left eye would actually have 2 very different images of the world. Now our brain doesn't show us 2 pictures. Our brain is a very incredible computer, and it kind of merges these 2 pictures together to give us one seamless view of the world. A quick, easy way to demonstrate this is to take your thumb, hold it out at arm's length with both eyes open, and then shut one eye, and then switch and shut the other eye. And you'll see how this image will jump back and forth. Yet, when we look at the world with both eyes, it creates one seamless image. Our brain just kind of merges the 2. But this retinal disparity gives us information about depth and distance. Another one of these binocular depth cues is called convergence. Now convergence typically comes into play with things that are very close to us. It's a neuromuscular signal. As our eyes turn inward to look at an object close up, convergence is another binocular depth cue. It's a neuromuscular signal. As our eyes turn inwards to look at an object up close, the muscles that turn the eyes send information back to the brain to show the angle at which the eyes are looking in, and that gives our brain information about distance. Look at the tip of your nose right now for an example. Let's move on to the monocular depth cues. If you had, if you played with that BB gun when you were a kid and you weren't supposed to, and you put your eye out, now you have only 1 eye. Does that mean you can't perceive depth? Well, no, there are many monocular depth cues. The first one of those is interposition. We have a lion, we have the car from Back to the Future, and in the back we have a very special kind of tree. Does anyone know what kind of tree that is? If you can tell me what kind of tree that is next class, there may be something in, maybe some extra credit or something. Something for you to figure out what kind of tree that is. How about these 2 playing cards? We have the King of Spades and the King of Clubs. Which one's closer to you, and how do you know? The next of our monocular depth cues is relative size. If we look at this tree, and then we look at the trees in the background, our brain interprets or perceives that these trees that are smaller are just further away. It's not that they're smaller. Experience tells us that if we were to travel over closer to them, that they would seem as tall as this tree. This picture here combines a number of depth cues and makes us see some very interesting things. It's actually an interesting illusion here. If we draw a line for this height of this man here, and we compare that to this man here, which man do you think is taller? Well, it's a trick. The images are the exact same, meaning the image on the back of your eye is exactly the same, yet our brain interprets it differently because of the depth cues that exist and our understanding of relative size. Here's another example. If we measure the height of this man and the image that it's placing our eye, and then we move that same size image right here, now in our brain we know that this man is not a very, very short man. It's just that he's further away, and our brain has to understand and perceive that. So, relative size and interposition are our first two monocular depth cues. Let's look at some more. Relative clarity, or texture gradients. When we look at this picture, we see that down closer to us, we can see a lot more detail and texture, and as we move off into the distance, we lose clarity, we lose that texture gradient, and our brain uses that as visual cues to distance. You can see the same thing in these pictures. Relative height. This one's a little harder. Students have a hard time with this one. When we look at this picture, things that are higher in our visual field we perceive as being further away. So as we move higher up in this picture, we perceive things as being further away. So one of these buffalo or wildebeest, whatever these are, that's often that's higher, physically higher, we perceive as being further away. Also, relative size helps too. It's not just relative height, it's also relative motion. Next time you're driving in a car, or rather riding in a car, don't do this while you're driving, look off to the side. Notice how things off in the distance seem to be moving slowly, but things nearer to you seem to be moving much faster, when in fact they're all moving at the same pace. It's just the perception of speed because of the distance is one of our depth cues that we use. This is also called the motion parallax. Another cue, or depth cue, is called linear perspective. I'm not a very good artist, but if you're a good artist, you know how to use these linear perspectives and these converging lines to give us a sense of distance. This makes it very clear if we measure this line. It looks like this white line down here is much shorter than the one above, but when we compare them, they're exactly the same. But the visual cues of these converging lines, this linear perspective, makes us feel like these are further away, and it creates this illusion with these two white lines, but it gives us a sense of distance in a 2D picture. And also light and shadow. And again, artists know that they can use light and shadow to give a sense of depth in a two-dimensional picture. So now we're back to our list of our depth cues, the two binocular cues and the 1, 2, 3, 4, 5, 6, 7, 8 monocular depth cues. Another thing that we perceive in our visual system is motion, and the ability to perceive motion. As things are shrinking and growing on our retina, the image, we perceive that as being motion. When we think about how film works, where we're seeing a bunch of still photographs, but it looks like movement because they're close approximations of each other, successive approximation, we get the sense of movement. Our brains perceive this movement and add it to our visual experience. Imagine if you couldn't see motion, if you could only see the world in still frames. How would that look? I'll finish with one interesting example of how the brain perceives motion. Look at these two rotating dots. Our brain is perceiving that rotation. But watch what happens when I add this. It stopped its rotation. Now this dot's just moving back and forth until I do this. So our brain perceives motion. It wants to see motion. It's kind of designed to see motion. Now we see a blinking dot. Now it's traveling. And now they're rotating. Make sure you check back for part 2 of our videos on perception.